Okay, so let us continue. Our final talk for today would be by Chuanzhong Li from Shandong University of Science and Technology, who will tell us about partitions in representation theory and integrable systems. Please.
Thanks. Firstly, thanks to the organizer to give me such a good chance to communicate with so many famous experts from all kinds of places. So my talk today is about partitions in representation theory. So these partitions, so I will study the generalization of partition and the refinement of partition and the S-duality of these partition. These are all connected with integral systems. So my talk will be separated into 4 parts. The first part is about additional symmetry. So integral system, if you use all of Solom's operators, we can get all kinds of symmetries like Virchow symmetry, block symmetry, and quantum torus symmetry, and so on. So if you let this Lie algebra act on the top function, you will get a very nice result from all kinds of field. So the second part is about the double partition. So one single partition corresponds to the third functions with a top function of KP hierarchy. If we generalize this into a double partition, we will construct a twisted Jacobi 2D. So this will be called the universal character. And also it will correspond to a universal character hierarchy, which is a generalization of KP hierarchy. The second part is about the solid graph. To classify all the solid graph or KP equation, we need to do the refinement of partitions or Young diagrams. So this will be called the Lie diagram. This is for singular Lie solidity. If we consider this is for regular Lie solidity or KP equation. If for singular, we need the Go diagram to do the classification. The last part is about the S-duality of partitions. This is related to Hessian finite dimensional integral system. It's a ODE. So we did we do a clear classification of some probable rigid surface operator. So let me introduce some background of Lie algebras. So this a linear space G, if we satisfy these 3 conditions, so bilinear antisymmetry and Jacobi identity, this will be called the Lie algebra. So there's a famous infinite dimensional Lie algebra, the Virchow algebra without centralization. So if this is one index Lie algebra. So if we generalize this one index to double indices, so this is a block algebra without the central extension. I remember some expert introduced this relation. U times V equal, if you switch order, then a Q constant appears. This Q sometimes called Planck constant or string couplet constant or Q deformed parameter and so on. There are a lot of names for this Q. If this is a quantum torus algebra, so MCAT, it has a double indices. So the coefficient depends on this constant Q. The power is M times L and N times K. There's a mixed product. So this is a quantum torus algebra without the central extension. If we do a normal order, so normal order always will create a central center. This is a central extension of quantum torus algebra. This is a KP hierarchy. This Lux operator is a pseudo differential operator. this D is a derivative with respect to the space variable X. So we have infinite time variables. So we can construct infinite flows. So this L operator, its tangent space is equal Lie bracket. This being is a positive projection for the L to its power. So this is the KP hierarchy. If this power is not from 0, it's from 1, this will create modify KP. And also, if from 2, of course, the Lux operator will change a little bit. It will become the Harry-Dim hierarchy. The Lux operator or KP hierarchy always can have a threshing structure. In the middle partial is corresponding to the trivial solution. So all the UI equals 0. So this is like so S operator make this trivial solution to general solution. This S, the tracing operator, very important. This S will satisfy a Sato equation. This Sato equation is equivalent to the Lux equation in the previous page. To construct the additional symmetry, we need the help of all of Schumann operator. This gamma is like this. So this Ti, this is contains all the time variable Ti. So we use this dressing operator to do a dressing to the gamma. So we can get all of Schumann operator M. So this Lux operator and OS operator M, this satisfy canonical relation like this. So we can construct the additional flows. If the flow is like this, M to M's power, L to L's power, to do the negative projection, this Sato equation will be a W infinite symmetry of this KP hierarchy. If we use another way, here we use exponential to M times the M operator, Q times the NL operator. This will become the quantum torus algebra. And we can prove these flows are all symmetries of KP hierarchy. That means they commute with the original KP hierarchy flows. But between among these additional flows, they don't commute with each other. They can constitute a nice structure like quantum torus algebra and many other algebra structure. So if we consider the top function, this so this structure Lie algebra can be you can treat it as acting on the Lux operator or dressing operator. If we consider representation on the top function space, so we need to introduce the top function. So this is a wave operator or wave function. So except this free function, exponential free function, there is a exponential eta. Exponential eta is a shift operator about the top function. So a top function do a shift, then over this top function, this will become the wave function. Adler, Ciotta, Pierre-Becker, they proved this formula. We call it the ASVM formula. So this log V, you take the additional flows TPS, you can get this formula. So this is the shift operator minus 1 acting on this function. Yeah, if we do we call it the W constraint, that means we ask this flow to be trivial. We freeze these additional flows, so this will become 0. That means this should be a constant, because the constant to a shift is also constant. Constant minus itself, it becomes 0. So we can get this. This should be equal constant. That means this W operator acting on top equals C tau. C is a constant. This is called W infinite constraint. It includes the Virchow constraint. So this top function have a lot of connections with a lot of field, including the partition function or who is member to the generating function. You can either satisfy some top function or reduction of KP, like weighting contractor, and also the matrix model. Also you do the to the integral. It also corresponds to top function. So the top function is very important. You know the top function, you know everything about the integral system. So we did some studies about these additional symmetries. So we found that the total hierarchy, we can get the block algebra structure, and also transfer the Sokolov hierarchy, and about the quantum torus algebra structure. And also we can generalize this block algebra to super block algebra. And B type and C type total, they can have a B type and C type block algebra. And also n equal 1 equal 2 super extension of this algebra are also interesting. And multi super integral systems and some disciplineless integral system, they also have this nice structure. So this is the first part of my talk. The second part is about the generalization of single partition. So in previous page, we the top function can have polynomial solution, and also it can have exponential form that it will correspond to Lansolitins. If we consider polynomial solution, you give if we have one partition. So this if we separate n into a sum of some primitive integers. So number one is this is the standard partition. Given this partition, we can construct a Schur function. Schur function inside the determinant, this h is from Schur polynomials, exponential this generating function. The coefficient hn is degree n Schur polynomial. Then this is called the Jacobi-Trudi formula. It's a homogeneous polynomial. It satisfies the Kp hierarchy. If you write the Kp hierarchy into a Hirota-Berliner equation. So Hirota-Berliner equation is in the middle between linear equation and nonlinear equation. So if it have a Hirota-Berliner equation, that means it's integral. So this is for one partition. We have a Schur function solution of Kp hierarchy. If we the natural question is for double partition. So lambda is one partition, another is mu. So we can construct a mixed determinant. For the several rows is about y. Y is a sequence of terminal balls. So x is another sequence. So for the first several rows, it's for 1 Kp Schur function. For the bottom several rows is about another Kp, but it have twisted like this. This is the mu for mu index. So mu is a second partition. So this is minus I. So this is plus I minus j. So here is there's a little different. This is R minus. So this mixed determinant will be called twisted Jacobi-Trudi. It was found in reproductions theory by Koch in 1978 in Advanced in Math. So this twisted Jacobi-Trudi described the rational representation of GLN. Schur function described the polynomial representation of GLN. So later, Chuta studied this universal character again and found the integral system who governed this homogeneous twisted Jacobi-Trudi. So they use a generalized vertex operator. What is generalized here? This X minus derivative with respect Y sequence. And here another vertex operator is here is Y minus derivative with respect to X, and this X minus dy, and this Y minus dx is commute. That's very important. Because they commute, so we can construct the universal character by this small vertex operator acting on the highest weight 1. You can get the homogeneous universal character. So for this another question is this universal character satisfy what kind of integral system? So Chuda found this using hierarchy. So if one function called xy satisfies this Hilbert equation, it will be called the UC hierarchy. This comparison between Kp and the UC hierarchy. So Kp is just have one sequence of temporal x, and for UC we have x and y. But they have twisted the gluing of these two Kp hierarchy. You will get a double Sato-Grassmann twisted gluing. With this will correspond to the UC hierarchy. So when a single partition is just one line, so you separate one natural number into a sum of several numbers. So the second one is about the 3D Young diagram. So every slice is a plane partition. So this corresponds to the crystal melting model. So you put some ice in the corner, it will melt. It will have this 3D Young diagram. 3D Young diagram corresponds to the Afan-Yang of GR1, and also it corresponds to the Jack polynomial. Jack polynomial is a special case. It is the top function of Kp hierarchy. This is a cylinder partition. So Bowden studied this. From cylinder partition, you can find the universal character. A special case, maybe two reduction, periodic reduction of this cylinder partition. So about the UC, we studied several intersections with other parts. Firstly, for quantum integral system, phase model, and the quantum Gaudian model, and the super quantum spin chains. So this quantum integral system, the T-master operator will satisfy the Hilbert equation of Kp hierarchy. So we glue two quantum integral system together to get a top function or universal character hierarchy. And from Lie algebra, so we can do a B-type and a C-type extension. B-type is the orthogonal UC and the symplectic UC. And also we construct another way to extend this Kp hierarchy. It's parasitic Kp and BKP and BUC, and the super BUC, multi-parameter UC. And also we can construct a multi-component UC hierarchy. Quantum field representation of UC. And also we calculate the Littlewood retardation rule of UC. So when two UC, you do a product, you have some separation of some UC. Yeah, this is called the Littlewood retardation rule. Also, as I mentioned, so 3D Young diagram corresponds to the Afan-Yang GL1. So a natural extension for two double index will correspond to the UC hierarchy. And from number theory, so we do an extension of Grossetti's type of extension. We will have another parameter beta to generate these prosthetics using. Recently, we studied the hop of link and find the hop of link, the generating function can correspond to the top function or UC hierarchy. This is a collaboration with Mironov and Orlov. And also, we studied the matrix model with correspond to the universal character. It is still in progress. So this is for universal character. It's an extension from a single partition to double partition. So someone will ask, how about the three partition? The result is no. There is no nice result for three partition. So only have two partition, which will correspond to this nice integrable structure. So the third part is about solid graph. This collaboration with Professor Yuji Katama and some of my students. So KB system, from the KB hierarchy I mentioned before, we can get 2+1 dimensional linear PDE. It's called KB hierarchy. KB equation. KB equation is one important shallow water equation. So if we do a transform from U to tau, law in tau take a second derivative, so this tau will have a very nice structure. It can have a Wronski. So inside the Wronski, every f function will satisfy the linear heat hierarchy. Linear heat hierarchy is easy to solve. So this makes the KP equation easy to solve. So we can set this f can have a linear combination of several exponentials. So this we consider the finite case, finite Lancelot. So important here is n by m constant matrix. So if you do a raw action, so this tau function will correspond to the same u. So every solution of KP equation will correspond to 1 point of gross money nm if we consider the finite case. So, but here we only consider the regular tau function because we need to take law and take a second derivative. Tau must be positive. So every minor of this n by m matrix should be non-negative. This is called totally non-negative gross money nm. So that's the object we will study. So we find so this every Lancelot is like water wave. So if we consider the asymptotic solution, so where is quite primitive, we have n Lancelotins. So for where is quite negative, we have m minus n, this number of Lancelotins. And how to give an ID for each Lancelotin? Here we will use the permutation group of SM. So this pair is a permutation group element. So for each fixed phi, so this pair should be derangement without a fixed point. If you have a fixed point, that means the tau function, you will have an exponential factor. You take ln, take second derivative, it will have no contribution to the u function. So we only consider this pair is in the derangement. It's a permutation group element without fixed point. So this asymptotic Lancelotins will correspond to a chord diagram. So this is for one to another. So this every point is every point will correspond to the spectral parameter of Lancelotins. So lambda 1 is smaller than lambda 2, smaller than lambda 3. We give one order to these spectral parameters. So this asymptotic Lancelotins will be 1-to-1 correspondence to the chord diagram. But inside, we can't see it clear. If we want to see inside the clear, we must to do the refinement of this. So every chord diagram will correspond to one Young diagram. This is one-to-one correspondence. This is a sympathetic solid graph, one-to-one corresponding to chord diagram, and one-to-one corresponding to Young diagram or partition. But if you want to see inside in the X region clearly, we need to do the refinement of to the partition. That's called the diagram. So let's see this picture. Because the KPA equation describes the cell water wave. So like this. So when Y is quite pretty, we have 3 line solitons. That means the 1 go to 1, 2 soliton. 1, 2 soliton means the spectral parameter is nominal 1 and nominal 2. 2 exponents of balance, it will create the peak of this line soliton. So the upper chord is when Y is quite positive, we have 3 solitons. When Y is quite negative, we have 2 solitons. Here, bottom, we have 2 line solitons. So this line soliton solution will correspond to this chord, So a symptotic line soliton have one-to-one correspond to the chord diagram. But we can see with time flies, so this in the middle, in the intersection part, it changed a lot. So, so this is the Kadama and Williams. They do a classification of regular solitons of KPA equation. They use a line diagram to do a classification. So this is a Young diagram. Young diagram will correspond to the top cell. Top cell means in the middle. Intersection part is the most complicated case. So that means you have a block structure, you have a box. So when this asymptotic line solitons, if they cross at one point, that's the most simple case. So this will be corresponded to the lowest dimension. So if this Young diagram corresponds to the top cell, if we wanted to get the lower dimensional case, we need to do the refinement. How to do the refinement? To add white box into the Young diagram. If you add more white box, that means the dimension will be reduced more. So this is the if Young diagram inside it's empty, that means we go 10 right or 10 left. If you touch the blackboard, you turn left. If you touch the whiteboard, you turn right. If you add a white box inside the box, white ball inside the box, you must go across this road. So you will get a tunnel. This is 1, 2. 1, 2 is the pivot or the A matrix. 4 is the pivot. So pivot always go down, and non-pivot go left. So you have 1, 2, 3, 4, 5, 6. These numbers you give these numbers are guided by the tunnel. So so these 3 will go out from through this way. So this 3 and this 6 they operate. So this will be a 3, 6 line solidity. So each number with the operator number, this pair will give an ID of each line solidity. So this is the line diagram. So we can see this in the middle. Every line solidity is clear because its ID will be identified. For example, this is 4, 5 line solidity. This is 1, 4, 1, 5 solidity. This is 1, 4. This is for regular line solidity. So each line solidity corresponds to a permutation group element pi. Recently, we studied this the singular solution. For singular solution, this line diagram is not enough. We need to use the goal diagram. Goal diagram, we need to add some black ball inside the box. So we can do a classification of the singular lansolidity. This is still in progress. This is the diagram. So this the upper graph about the numerical study of this wave type inertial data. You will see it will create a parabola. This parabola will grow stronger and stronger. When t go to infinite, this parabola will become the complete lansolidity when t go to infinite. The bottom three graphs pictures is the regular solution of this is 3142 lansolidity. We will see that in the middle, there is a very higher amplitude one solidity. We call it the 1,4 solidity. 1,4 solidity because this 1,4 is from kappa 1 to kappa 4. This is the biggest gap. Gap means the amplitude is the highest. So we can't see this 1,4 solidity from this chord diagram because this chord diagram just describes a symptomatic behavior of this Grassmann 2,4 lansolidity. But we can study how this parabola grows. So that will correspond to the chord dynamics. So some point will move with time goes on. So firstly, the initial data is 1,3 solidity, and the bottom is 2,4 solidity. Later, it will create a 3,4 solidity and a 1,2 solidity. This generating new solidities will satisfy a minimal energy rule. So each gap will denote the energy of this chord. So the totally energy should be the minimal. Then it will create a 1,4 solidity. This is called Mach stem. Sometimes they call it rogue wave. This is a special. This graph is a numerical. The arrow. You can see when the time goes on, the arrow will become lower and over is almost touch zero. Recently, we studied so this is for Kp. If we do a reduction of 2 reductions in KdV, 3 reductions in Bosnisk, and also it can have any reduction. This is called gap and decay reduction. So for Bosnisk, we can find it can have only one Y-type lansolidity. This is only for regular. If you have more than one Y-type solidity, it must be singular. So every for example, this Y-type solidity, you need to choose 3 type point of this cubic curve. So for KdV, it's a parabolic curve. For Bosniski, the cubic curve. For reduction, you have for any reductions, you will have more highest power curves. So every time you choose one several points, you get a sub Grassmann manifold. You glue them together. But if you gluing, it must have no crossing. Otherwise, it will become singular. That's why we only have one Y-type lansolidities. Others are just the one solidity inside. So these ones. So every one corresponds to one different curve. So this is our new result. So when you gluing this, this I forgot to mention. This is cycle notation of permutation group element. So the A1 go to A2, A2 go to 3, A3 go to A1. So that means this 1 go to maybe 3, 3 go to 2, 2 go to 4. This is Y-type lansolidity. This is the level we studied the chord dynamics for if you study the initial value to do the evolution for Kp equation. And also, so we do a complete classification on regular gap and decay solid solutions. For the regular case, it's still in progress. So this is the second part of our study. It's about the refinement of partition. The last part is about the S-duality of partition. So as you know, if we unify the electric and magnetic field together, it will be called electromagnetic field. It's also called Yamya's theory or Gibbs theory. In Gibbs theory, they have a lot of symmetries. These symmetries are always described by Li group. So S-duality is about the duality for G Li group to its Lagrange and dual group. And also tau go to 1 over tau. So one side, if the series about the tau, it's a conjugate, divergent, but the other side will become conjugate. Yeah, that's why they studied the S-duality. With this duality, you have a T operator and S duality and T duality. S duality are more important. For A equal 4 super Yamya's theory, if here you have 4 variables, but we only consider the 2 variables of them. This is called the surface operator. So super then A equal 4 super Yamya's equation will become the Hessian equation. Hessian equation for A and phi. So this is the Hessian equation. This star operator is a Hughes star operator. It maps from one form to one form, and all 0 form to two form. So Hessian equation, if you do a transformation, let x2 plus I x3 go to I times the exponential I theta. Then we do ansatz. So for A, here is di, the coefficient of di becomes 0. Then the Hessian equation will become the normal equation if we do a transformation for R to S. So this is normal equation. Normal equation is a finite integral system, but they always care about this solution. So here ABC, if this Tx, Ty, Tz, they satisfy they can spy the potential was SU2, then this ABC will naturally satisfy the normal equation. So for different type, for B type, C type, and D type group, the difference is this Tx plus I, this will have different part. So each part have the block, the size of block is A1, A2, NL. So for different group, the difference is in the partition A1, N2 to NL. So for example, so for nilpotent orbit, so Bn should have this property. So the sum is odd, and even integer appear an even number. This is for Bn. C and D have other requirement. So we found we need to add the rigid condition to make the set closed. So what is the rigid condition? The first one is no gaps. That means lambda 1 minus lambda r plus 1 should be not bigger than 1. And also no odd integer appear exactly twice. So this for B and D. For C, this even integer appear appeared exactly twice. This is the rigid condition. After this rigid condition, we can find B, C, D they have a different requirement for partition. For BA, so the bottom one should be odd, then pairwise. So for each pairwise rows, they can be both odd or both even. They must be have the same parity. So for DA, the bottom one is even. So for BA, if it's you have one more rows, the top row should be even, and also for C always pairwise. So this is the requirement for the partition for B, C, and D. For the semi-simple case, it will be separated into two parts. So B will become the B plus D. Then D is D plus D, and C is C plus C. So this is for then this is for rigid semi-simple surface operator. We will have two partitions. Gukov and Waiting, they found this rigid surface operator. They found some invariant which do not change under the S-duality map. The simplest is the dimension D. Here, this prime and double prime means the first partition or second partition. This S means the number is larger or equal this K. And this and R means equal this K. So this invariant is very simple. It's not so interesting. The most interesting tool is the fingerprint and symbol. Fingerprint, this invariant is a double number sequence, alpha and beta. So for this pair of partitions, we can construct the invariant alpha beta. This is called fingerprint. This is from the Kazan-Lustig map. And another invariant is a symbol. Symbol is from the spring correspondence. This is a map from a unipatent conjugate class to a unitary repetition. So let's see the definition of these two invariants. Symbol invariant is defined like this. I just mention the definition for B type. For C type and D type, it's a little different. So for B type, so we L is the length of the partition. That means K plus lambda K. We'll get a sequence of numbers. We pick the odd number out and the even number out. We get FR and GR. Then FR and GR we can generate alpha R and beta R. So this will generate two sequence of numbers. So this is called symbol invariant. Symbol invariant, for symbol invariant, we find our calculation is we find a very simple calculation. We can calculate each contribution, the contribution of each row, then do a summation of all the contributions of all rows. We can get the whole symbol of the partition. So, so for t equal -1, t equal 0, and t equal 1, these three numbers will correspond to the B type, C type, and D type. So for the length of ith row is odd, even, and I plus T plus 1 is even and odd. This L is the length of the boxes. So we can calculate the contribution of each row and do a sum, vector sum. We can this calculation is much simple than before. Using this calculation, we can this is one example of the S duality map. This map is from B type partition to C type partition. This M must be odd. The first one is the B type. Second, the target is C type. So this map preserves the symbol invariant. And every duality map changes these two partitions. One is from G Lie group, another is Lagrange dual Lie group G L. So this is another example. For unipatent case, means just one block. So the second one will be okay. Then from B type, then at last we use this X map acting on the old partitions. We get a C type. This is one example for B6 and C6. That's SO13 and SO12, SP12. We can find some part are missing. For example, for this partition, these are all rigid partitions. Its duality is missing. So Witten found maybe from B4 or C4, they found some duality are missing. So this column is a dimensional environment. This is symbol, this fingerprint. So what we did is we do a classification of all the probability surface operator. We give the condition. They satisfy this condition. It will have no duality. And why they don't have? Sometimes because the first rigid condition, sometimes because the second rigid condition. We construct a lot of algorithms to do the classification of the probability surface operator. This is another environment, fingerprint environment, quite complicated. You do I will not introduce in detail. So it's very complete. So I will tell you, you don't need to calculate the fingerprint anymore because we can prove this fingerprint is equivalent to the symbol. So the proof is in our paper here. Because the symbol is more simple, so fingerprint are more complicated. So I think that's all my talk. Thanks.
Thank you very much. Are there any questions? We have time for 1-2 quick questions.
So the universal character case, and you have binary equations. Do you have this explicit form for the binary equations, or just the formal?
Yeah, for universal character hierarchy, you cannot get a simple closed equation like a KP equation. You can't, because you can't truncate. Every equation it has infinite terms. So that's but this universal character hierarchy have a lot of connections with all kinds of Pauli equations in different Lie type, Lie algebra type. So that's very interesting.
Other questions?
Hi. So you mentioned that you have work in progress in relation to matrix models.
Yeah.
Yeah. Can you just comment what sort of models you have in mind?
Sorry.
What sort of matrix models?
Oh, what sort of matrix? So we have I think we use a unitary matrix, and I think several kinds of matrix models. Because KP, you have a lot of corresponding matrix models. For each matrix model corresponding to KP, we can generalize it to the corresponding type matrix model for UC. I think it have KP have.
Okay, yeah.
What KP have, then UC also have.
Okay.
All right, more questions?
So, yeah, quick question. So I wanted to ask, what do the crossings and nestings in the chord diagrams for permutations count in solitons?
Yeah, that crossing can keep the gluing. So regular here. Wait. So for a big lansolitins, we need to gluing some small group of lansolitins together. So each small group of lansolitins, they are regular, but when you gluing them together, sometimes it's not regular. But this non-crossing condition can keep this gluing can keep the regular condition.
Okay. And I mean,
otherwise, you will it will be regular in some region.
And out of curiosity, so the crossings and nestings are equidistributed, right? I mean, they are symmetric. So I was wondering if you have another model where you get Boussinesq equation. I mean, you have some family of permutations where instead of crossings, you only have nestings, and then these, equivalent some sort of via some bijection.
Yeah, this non-crossing means the chord diagram no crossing. So for example, for one group of lansolitins, you have a chord diagram. For another group of lansolitins, you have another chord diagram. But if you combine them together, sometimes you have crossing. Each crossing will change the regular condition. Regular becomes singular, singular becomes regular. Yeah, we are studying in this in detail about the singular, regular. Sometimes singular in one soliton part is regular, then changes singular, then change to regular again, and switch. So how this switch? That's what we are studying now. Very interesting.
All right, well, thank you very much.
Thank you.
Let's thank the speaker and wrap up for today.